The title of this note is Rate of Change in Tangent Lines. Make sure you put your name, date, and class period in the top right-hand corner. And the essential question that you'll be able to answer is, how does the difference quotient calculate instantaneous rate of change? We've got two vocabulary words. How does the difference quotient calculate instantaneous rate of change? So slope, we've talked about, is a rate of change. Slope is a rate of change. And so we've talked about, how do we calculate the average rate of change? That's the rate of change between 2 points. Well, we can replace the words rate of change with slope. So the slope between 2 points. If we think back to our middle school algebra days, we have our slope formula. And remember that y is just the output of the function. The x is the input and the y is the output. So I can rewrite outputs as f of x. So f of x2 minus f of x1 all over x2 minus x1. It's just another way of seeing the slope formula. And this right here will calculate the average rate of change. And we're going to abbreviate change with a delta. So how do you find a tangent to a curve? To find a tangent to a curve, you're going to first find the slope of a secant line. So let's just touch back on vocabulary. Here's a curve. The tangent line only touches the curve at 1 point. But we need 2 points to calculate slope. So instead, we're going to use a secant line. I'm going to do that one in red. A secant line is a line that touches at 2 points. So the red is an example of a secant line. So you're going to start with the secant line, and you're going to find the slope of the secant line. And then what you're going to do is you're going to bring the endpoints. This is x1, this is x2. You're going to bring them closer together. Eventually, the distance between them is 0. So you're going to bring them closer and closer together. And as you bring them closer and closer together, your secant line, I'm drawing it here in red, is going to get closer and closer to your tangent line. So when you are asked to find the slope of a curve, what that means, it means the slope of the tangent line, right? Because slope is for line. So in calculus, when we talk about the slope of a curve, what we really mean is the slope of the line that is tangent at that point. Okay, so we're going to actually do an example together. So I want you to find example 3 on page 89 of your textbook. And we're going to find the slope of the curve, y equals x squared. We're going to find the slope at the point 2, 4. 2, 4 is a point on that curve. So if I'm thinking of a sketch, x squared, I could put it in my calculator, it's just a parabola. And then here's the point 2, 4. I'm going to label that. Okay, what is the slope of that curve? So let's think of the tangent line there. Okay, so what we're going to do is, instead of finding the slope of that tangent line, we're going to find a slope of the secant line. So I'm going to choose a second point. And I'm going to say that that second point is h away from the first point on the x-axis. So the first point is at 2, 4. So the second point, the x-coordinate is 2 plus h, where h is just a little bit more. 2 plus h. So then what's the y-coordinate there? At that point right there, that's 2 plus h. What's its y-coordinate? Well, to figure out its y-coordinate, I'm going to go back to the original equation. And I'm going to do this in black over here on the left. The original equation is y equals x squared. Now x is 2 plus h. Okay, so 2 plus h squared. I'm going to FOIL that out. That's 2 plus h times 2 plus h. So I'm going to FOIL that all out, and I'm going to get 4 plus 4h plus h squared. So that is the y-coordinate at that point. And I found it by putting 2 plus h into the original equation. 4 plus 4h plus h squared is the y-coordinate. So now I have these 2 points that are really close to each other. They're each apart on the x-axis. Now I'm going to use my slope formula, where if this is x1, y1, this is x2, y2. So the slope is y2 minus y1 all over x2 minus x1. Now I'm going to simplify. 4 minus 4, those cancel out. So then my numerator is 4h plus h squared. And then in the denominator, 2 minus 2 cancels out. My denominator is h. Looking here, I have a GCF. There's 3 terms, and they all have an h. So I'm going to go ahead and factor out that h. And that's going to leave me with 4 m equals, that's what that's supposed to say, m equals 4 plus h all over 1, but you don't need to write all over 1. Okay. Now, remember, h was just a little bit. And eventually, those 2 endpoints, we want them to be 0 apart. So eventually, our goal is for h to be 0. So what we're really doing here is we're finding the limit as h approaches 0 of 4 plus h. And that will be 4. So the slope at the point 2, 4 is 4. So what we're really doing is we're taking our slope formula m equals f of x2 minus f of x1 all over x2 minus x1. And what we're doing is we're saying, okay, take x1 and let x2 be x1 plus just a little bit more. We're going to call that little bit h. So that's going to change. Here, I'm trying to get you to a formula. So here's what I'm going to do. I'm going to call x1 some point a, and I'm going to call x2 some point a plus a little bit more h. And what that's going to do is I'm going to replace x2 right here with a plus h. So I have f of a plus h minus f of a, because I'm replacing x1 with a, all over x2, which is a plus h, minus a. And I want you to notice that in the denominator, a plus h minus a will always simplify to be h. So a new way to find slope is this formula here, f of a plus h minus f of a all over h. And like we just saw, our goal is to get the 2 endpoints really close to each other, so our goal is to get this h closer and closer to 0. So another way to find slope is the limit as h approaches 0 of f of a plus h minus f of a all over h. And this here is called the difference quotient. Difference because we see subtraction, quotient because we see division. This is a very important idea in calculus. You'll hear the difference quotients referenced a lot. So every time you hear difference quotient, you're imagining this formula here. A few more things to talk about in relation to tangent lines. We have something called a normal line. A normal line is something that's perpendicular to the tangent line. The key here is to know that your slope is your opposite reciprocal. So if we think back to our last example, we just saw that for y equals x squared, at the point 2, 4, the slope was 4. So that would be the slope of the tangent line. If we want the normal line, we're just going to take this original slope. I'm going to imagine it's a fraction, 4 over 1, and it's a positive. So it's going to be negative 1 over 4. So that's the normal line, negative 1 over 4. The tangent line is 4. And those two are perpendicular. Last quick idea, we want to talk about speed. speed is the absolute value of velocity, because velocity shows direction. So velocity can be positive or negative, depending on if you're going north or south, east or west. But speed is always a positive number, right? If you're driving down Route 2, you're always going 50 miles per hour. Doesn't matter if you're going north or south, but your velocity would be positive 50 if you're going north, negative 50 if you're going south. Speed and the positive velocity, they are just the instantaneous rate of change of position. That's how position and speed are related. So your position is measured in feet. And if we were to graph your position, we would measure your feet over time in seconds. So the rate of change, remember, is your slope. So the slope would be the changes in the y's over the changes in the x, right? This is just a fancy way of saying y2 minus y1 over x2 minus x1. The y is getting measured in feet, and the x is getting measured in seconds. So looking at our unit analysis, feet per second is a way of talking about velocity, and it's the slope of position. That is the end of our notes. Go ahead and put your line for your summary, and we will finish that in class.